Hello, we are going to present our research paper titled A Physics Logic Model Based on Web of Trust to Access Linked Open Data Resources. We are from Universidad Distrital Francisco José de Caldas and Fundación San Mateo, Bogotá, Colombia. The relevance of the linked data and linked open data have been endorsed for many years in many scenarios, even governmental institutions, as long as it responds to a factual need of these times. Different authors have presented some strategies to show semantic web information with an organized structure capable of doing analysis in the business process in the organization, so that there will be greater control and a knowledge of the behavior and trends of the Internet. One of these strategies is the Web Access Control, which proposes very complicated restriction using a method known Privacy Preference Ontology. The WAC mechanisms currently used by LOD allow you to create access control lists, which basically allow the user who posts the information to filter the user who can see the information. Other of these strategies is based on OW language to define security mechanisms that allow to authenticate user and access certain information through credentials. Currently, there are researchers that have applied the security principle based on the control access and security mechanisms. Still, some research improved the use of security based on Web of Trust principle directly of metadata and content resource of LOT. In this context, our research problem was how to improve the quality dimension in the metadata and the access to the resource of LOT based on Web of Trust principles. For that reason, this research proposed a security model based on physics logic rules to access linked open data resources with trust principles. The purpose methodology to develop the security model based on physics logic rules to access linked open data resources has 8 steps, which we are going to describe below. In the first step, we select both visual notation for OWL ontologies. This tool is a well-specified visual language for the user-oriented representation of ontologies. In order to design a security model based on the trust principle for the consumption of logged resources, it was proposed to extend the functionalities of both through the design and implementation of a model based on physics logic, which allow to obtain information about the time uses in the batch query process of the logged resources exposed. This information was considered as keys based on the trust principles in the access to logged resources. For the model design, we set up to work with Type 1 physics system with a logical rule design. For this purpose, we use two variables obtained from the query component of the logged resources. First, the number of the successful requests over the total number of requests on one query. And second, the average response time taken by each query run in resolving data consumption. For the Type 1 physics system, these variables are structured in the form of antecedents, which are represented as sets and are used to obtain a decision completed in the consequent sets. The choice of this approach is based on two premises. One, in the environment of uncertainty generated when querying datasets, and second, the need to solve this uncertainty with control over the operation of the system. The next step was variable definition. In this step, we identified two variables which are present in the logged resources visualization process. The first, NSR, number of successful requests. This variable corresponds to the proportion of requests that are successful at the moment of making a query in order to work with the requests that are part of the query process and give a response at the runtime. The second, RT, response time. This is the time that has taken the application to respond to an associated query, given that these queries are about load resource visualization. This variable is measured in seconds and allows us to work with the time that correspond to each query during implementation, the execution. The fused set associated with the membership function was established for the antecedents and the consequence of the system through the definition of concepts that will measure the uncertainty that contemplates the system to make decisions in the execution time. The sets are shown in this table. The attributes were defined for the definition of sigmoid sets in terms of antecedents and Gaussian in terms of consequence, taking advantage of their characteristic of continuity and derivability. These attributes allow us to understand the behavior of the membership function associated to each of the fused sets proposed in this table. The fused sets were defined in the antecedent and consequence dimension. For the antecedents, this graph represents the purposed membership function for the management of the concept that can be given at the moment of the implementing the fused logic model. In both scenarios, if we use logistic sigmoided sets described above, so that they can be grounded runtime arguments that have not been experimentally completed. For the consequence, the graph handles the purpose concept to describe each of the member functions in terms of the performance associated with the query. This graph works Gaussian sets so that it is possible to make a diffusification that can be associated with a concept declared during the postulation of the concept in the fused logic model. We designed the logical rules of the system taking into account the use of Mandani's mathematical model for the implication of the logical conditional. In this example, P is the antecedent and Q is the consequent. The design of the logical rules allows us to associate a decision to each possible scenarios with the aim of provide the implementation of the fused logic model, taking into account the flexibility provided by the network with type 1 fuzzy system. In terms of the antecedents and the consequence proposed in the fused logic environment, the system receives these variables as arguments and makes the decision as appropriate in the set described in the consequence. For the design and implementation of the proposed experiments for the model, the following aspects about the system were defined. Number 1, discretization or postulation of value. Number 2, fusification using singleton. Number 3, rule aggregation using the Mandani model. Number 4, diffusification with average center weighted or centroid. Number 5, link with functional components. Considering the use of the antecedents in the system to grant a decision, in the implementation we classified the result of the consequent in 4 categories. Number 1, optimal performance. Is the best possible running scenario. This performance scenario could be considered as the ideal scenario in a load resource consumption environment. Number 2, average performance. It corresponds to the most standard scenario of the implementation, being an environment of uncertainty. This scenario of performance is the most commonly known when consuming load resources. It denotes that they need defined level of trust for consumption. Number 3, deficient performance. This performance scenario is similarly known as the average performance since its results are unattractive when consuming load resources, so that the implementation of the fused logic model from this point could consider more representative fields over the results. And number 4, critical performance. It is the worst possible scenario execution. During the research process, a number of rules based on fused logic were determined, which, through collection and analysis of input, allow a first level of trust to access linked open data resources. As a result of this analysis and collection of this input, we obtain the results whose objective is the visualization from both, together with the described operation of the fused logic components and the rules built to give level of trust. This figure displays the components established by both from their visualization. These correspond to URL, pending request, successful request, and failed request. These results and the validation of the proposed model based on fused logic are detailed in the next figure. In the next figure, you can observe two variables. Number 1, times, is the list of the overall average of the time that the query is delayed. And number 2, performance, is the index of work obtained for each query adjusted to the fuzzy sets designed. Each of these visualizations corresponds to the consumption process of the different endpoints. The performance indicator, PI, shows us the performance based on the work of the fused logic component. If the PI have a higher percentage value, the selected endpoint have reached a higher level of trust. As a conclusion, visualization of linked data can provide a useful starting point for query and analysis of data consumption. There are few works related to the extraction and visualization of information schema from linked data, for example, a knowledge pattern and key concepts. The design and consumption of a Type 1 fused model using a logical rule set provides element and security model to access the results based on trust principles. The evaluation of variables such as number of result requests and response time in the query process of load resources allow a better analysis using inputs and valid factors for making decisions, thus determining a level of trust more useful and assertive. Therefore, the use of fuzzy sets allows the identification of variables such as PI in scenarios where there are big data consumptions. These criteria, in their classification, optimal, average, deficient, and critical, will provide us with analysis tools based in level of trust when you want to have an experience of consumption and query of some available log repositories.